Okay guys, the purpose of this video is to give you guys a bit of an overview of my off-grid setup. Firstly, this is my 15 kilowatts of LG panels, which is separated into 5 kilowatt, 3x5 kilowatts using Electronic certified ABB inverters. Ignore the weeds there. They are AC coupled into my SP Pro, which you can see here, and we'll come back to that. So here you can see the battery bank. This is a 120 volt system. There's a total of 40 parallel sets of cells laid in 10 by 4 configuration. You can see the 4 rows there by 10. If I come down and we can have a look at some of these individually, and each one of these, if I can get the light right, is made up of 5 individual cells. These are high power branded cells. High power doesn't exist anymore, but they seem to be going okay. Each of them is 180 amp hours each, and therefore each one of these little banks that's strapped together using backing on both ends of plywood and pallet strapping totals 900 amp hours at a maximum voltage of 3.6 and nominal 3.2. It's using an lithium-ion BMS. Now you can see, if I come closer, this is a cell board, and you see that one's a red one, and you can see that that one's a green one. So the way that this is working is that each of these shelves is considered to be one bank by the BMS. So if I come back to the BMS, you can see I've got 4 cables coming in there, 4 banks. Each one of those banks is one of the shelves coming through onto that side. So just coming back, so on each bank there's a positive end cell and a negative end cell. In this situation we have, I think it's a positive, I don't remember off the top of my head, and basically what happens is a single wire that comes into there, which you can see that grey one coming down comes into there, and then it joins via a single wire to the next one, which you can see going along there. Then that's clipped to the single wire going all the way along, and then at that end you can see it's attached to the grey one going back. Now each of those cell boards is responsible for monitoring the voltage and the temperature of each of these parallel banks. When they're connected in parallel, they hold each other self-balanced when they're connected in parallel, and you can see that they're strapped together in series using copper strapping. I didn't have enough of these straps to do those interim ones, so I got a friend to CNC some copper straps to go across each of the banks, each of the cell sets, if you will. Now, it's also, these little cell boards are responsible not only for monitoring the temperature and the voltage across each of these little parallel sets, they're also responsible for managing the balance. Now, they're only capable of a few hundred milliamps, which is not enough to do this big 900 amp hour thing, which is why these balance boosters are installed. And basically what happens there is the positive end is simply connected to the positive of the cell set, and the negative to the negative, so that's easy. And then there's a white control wire that extends from the actual cell board, which you can see there, and so when that goes high, it tells this to dissipate some power. And each of these, and they're connected in parallel, so each one of those boards is capable of an average of 2 amps each. So I can basically, what happens when that thing turns on, goes high, you actually see 4 amps, approximately 4 amps getting shunted across, which is a solid amount of balance. And obviously when it's balanced enough, that'll go low and it will stop dissipating. The downside to that is obviously 4 amps multiplied by 3, that's 12 watts of power. And when you multiply that out, excuse me, by 40, if they're all balancing at the same time, well, let's say half of them are balancing, that's you know, a good couple of 100 watts of heat energy being dissipated. It's the same basically as a 200 watt heater. So you can imagine in summer
that can get hot, in addition to the fact that there's sun radiating on the outside. So there's insulation panels, and I've also got an air conditioning system. So you can see I've got a caravan air conditioning system that vents to the outside, and that actually comes through at the bottom there, you can see, and pumps across the bottom cells, and there's room around the sides, and at the top I've actually got some fans which does back pressure, so it pulls as the cool air comes in at the bottom, it pulls the hot air back out at the top, recycles back down through the air conditioner and back through the system. Excuse me. So that's the banks. When I started out, I didn't have any. Well, I had some older balance boosters which weren't as good, and they fried, and I didn't realise, and so it wasn't balancing properly. But since I've installed these newer versions, it's working really well. So that's that. The only other thing I'll add to this is I did use some special goo on all these terminals to improve the contact, and I'd suggest that if you're building one of these systems, there's a special, it's been 18 months since I used it now, so I forget the name of it, but it's a special electrical conducting thing, liquid that you can stick on, and you can see a little bit of it in the contact there, which also helps. Okay, so coming around to the BMS, so what we've got in here, this is the E-lithium BMS. So what's happening here is that it's got all of the cell boards connected to it at the banks. It's got a USB to RS-232 coming up to a Raspberry Pi, which I'll come back to. It's got the external current sensor coming down into my contactor area, and it's got some control systems related to the contactors as well as an on switch. These contactors, one is designed for high limit, so if any of the cells exceed a high limit, it shuts off charge current going to the batteries, the battery bank, and the other contactor is for the reverse, so if any cell gets too low, it shuts off any discharge. And there's actually some very high power, highly rated diodes in there that are capable of a large amount of current, and to basically allow current flow one way through the discharge contactor and the other way through the charge contactor. There's a circuit diagram for this setup on the E-lithium website, and you can see that that's the current sensor there, and this is a 12 volt supply that's also connected directly into the battery system. So even when the inverter is off, the BMS is powered directly from the 12 volt supply coming from the battery system. And this, as I said, the circuit diagram for this is on the E-lithium website, and it works reasonably well. The downside, if you will, is that as soon as these contactors go, the whole system goes down, because this electronic box relies on an always on battery. And so if the BMS decides I've had enough and shuts off one of these contactors, then this electronic goes down, and obviously the power goes out and it needs to be manually intervened, and it's a bit painful. So the idea is these contactors should really be a last resort, not a control system. I originally thought they would be a control system, but really they are a last resort. They are, I would definitely suggest, don't skimp if you're building a system like this on these contactors. You want to get ones that are rated for a large number of breaks and much higher current rating and really high temperatures, because you do not want those to weld, because if they weld, you basically toast your pack, because the BMS has a final say, and when you're charging at say 20 kilowatts of power, if the BMS says stop and the electronic for whatever reason has a heart attack and disagrees, you want those contactors protecting your pack, otherwise it's toast. We have a battery sense, so again this is a direct connect to help start up this electronic SP Pro, and the more details on that you can find related to this electronic device, and obviously the main DC breakers between this electronic box and the battery bank via the contactors. Now coming up to the Raspberry Pi, this is used for a few purposes. Firstly, it's constantly monitoring the cell voltages via the BMS, so the BMS is reading it, and then you can see every second I'm using the Pi and a Python script to read those voltages, and it's also, the BMS outputs a signal that says charge limit and load limit, and that's a very complicated function that it performs based on its calculation of balance requirements, cell voltages, and also temperature, high and low temperatures. So it does all that logic and says you should limit charge to 80%, 90%, 10%, etc. of maximum charge rate. So I can read that into here and go, okay, well, if it's asking me to limit the charging as it gets full and it starts balancing to say 50% of maximum charge rate, I then use the Selectronic charge profiling to manually trigger. So the Selectronic is not really designed for lithium at all, but it does have these 4 charge stages: initial, absorption, float, and equalize. And there's actually the 4 that you can program is initial, separately bulk, separately absorb, separately float. And so you've got 4 different set points that you can set for charge current. Excuse me. And so what I've done there is I've said you can actually set it up and feed control signals into the SP Pro, saying, okay, trigger it to go from initial to bulk, trigger it to go from bulk to absorb, trigger it to go from absorb to float. And so all I do from the Raspberry Pi is I send a control signal via a relay to get it to 12 volts into the SP Pro board to digitally trigger it to go across. So the SP Pro's, all its fancy programming around charge stages is completely ignored and entirely controlled by the Raspberry Pi, which is reading from the BMS. In other words, it'll charge flat out. It'll just say, give me as much as you possibly can, 15, 20 kilowatts, until the BMS says, okay, start to slow down. I'm seeing a cell reach its limit and I need to start balancing. And so as soon as that happens, the Pi goes, yep, no worries, and digitally triggers this to enter the next stage, which drops the charge current down a level, and then when it gets even further down, we go to the next stage. So there's 4 stages. Ideally, you'd want a clean linear dial back, but it's not possible with the Selectronic, and so we just manually dial it back in 4 steps until we're done. This BF430 thing here is me extending. We've also got an extra 5 kilowatts of panels on a roof that's further away on our property, and we're using an IP connection to drive, instead of having an RS485 connection to the ABB inverters, we're using an IP connection to get down there, and this is an RS485 to IP converter. So that's that. Now the other thing that the Raspberry Pi is doing, in addition to reading the charge limit controllers, is it's also reading the battery health information and voltages, and it's also reading, as you can see, from the SP Pro itself. And so I can then take all that information and then also upload that to our PV output. And so it's doing that on a 5-minutely basis as well. So it's doing the job of both controlling the charge coming in and also uploading to PV output. So that's it, guys. There's a few other things that I'm working on for a project. I've got to tidy up this AC to be automatically triggered. I'm currently using a Sensibo device to manually turn the AC on and off remotely via the internet, but I want to control that to be automated based on temperature signals and then also control these fans via son-off devices via AirPlay, but that's something that I'm still working on. So I hope you guys enjoyed this little video and got value from it. If you're looking at building a system, happy to help out if you have any questions. Otherwise, have a great night. Thanks, guys. Bye.